Hello everyone, this is Aditya and today we're going to study partial differential equations in one shot. But before that, I want to clarify one thing, that I have my flight in like 3 to 4 hours. So that is why half part of this lecture will be recorded on this board and the next part will be recorded on another board in NIT Durgapur. But of course, they both will compile in one lecture only. So you don't need to watch two parts, right? But just I want to clarify that the board will change in next half, okay? So now let's start with the lecture. But for that, please do like, share, subscribe my channel and please support this video. Now let's start. Now, what is meant by partial differential equations? Well, if you must have studied ordinary differential equation, then you must know that in that case we study one dependent variable and one independent variable, the relation between them, right? But in this case, we'll be studying about one independent variable and two or more independent variables. So one dependent and two or more independent variables. Suppose z is equal to 3x plus 2y square. Let's assume this, okay? Or simply y square, right? So if I say you to differentiate it with respect to x, then you will get dz by dx will be equal to 3. Why? Because x and y are independent variables. So that is why when you differentiate it with respect to x, then of course y is a constant because they both are independent, right? And when you say dz by dy, you will get 2y, right? Correct? Why? Because with respect to y, x is a constant, right? Because they both are independent. So instead of writing d, we use a term del z by del x is equal to 3 and del z by del y is equal to 2y. And this is the basic introduction of partial differential equations, basically how we solve such kind of things and how we form them, right? Of course, we will dealing with more. This is just an introduction, that what is meant by it, okay? So basically, these are the functions that z is a function of x and y, of course, right? Correct? Okay. So it tells that it tells the gradient with respect to x and it tells with respect to y, right? So that is how we solve, means this is how we represent the functions, right? So of course we are going to see further that how we solve them and how we form them, right? This was the basic introduction, that why, that what is meant by actually these partial variables over here. Okay, so this is the dependent, this is the independent, this is also the independent variable. So you can have multiple such independent variables in this case, for example x1, x2, x3 and so on and so forth, where x1, x2, x3 all are independent variables, right? Understood? Okay, so let's erase this and let's move into the definitions. Now let's write some definitions, that a differential equation which involves partial derivatives partial derivatives are called partial differential equations. Well, it's simple. We know what is the differential equations, right? We know we studied in ordinary differential equation. You can check that video, right? So which involves partial derivative, that is del z by del x or del z by del y and so on and so forth, right? Such derivatives, if they are involved, then it is called a partial differential equation, right? Okay. Now, yeah, there can be many examples. For example, x del z by del x plus y del z by del y is equal to z, right? And suppose let's take some examples to understand some concept. We will discuss it just a minute. Okay, and another example we can take del 2z by del x square plus del 2z by del y square is equal to 0. And suppose del 2u by del x del y is equal to del u by del z whole cube, right? Okay, so why did I give three examples? I could have just given one example to explain it, because I needed to explain something called order and degree of a partial differential equation. Correct? Okay. So basically it is equal to, it is the order. Of course, you know what is meant by order. You have studied in ordinary differential equations, right? You can check that video if you don't know that. Okay, of highest derivative, highest ordered derivative. You can say ordered derivative. and it is the degree of highest order derivative. So let's understand it using this example. So in this case, we can see that it is just del z by del x and del z by del y. So it means that only one times this is involved, this operator. So we say that its order is equal to 1 and its degree is equal to 1. Why? Because there's no power involved, it's just one power. Of course, this is raised to the power 1, raised to the power 1. Simple? Okay. Now see this, in this we have second order, this 2 and this 2 and this 2 and this 2. So it is order 2 and degree is 1 because it is raised to the power 1. Correct? Okay. Now notice one thing, that in this case order is equal to 2, but many people get confused that degree will be 3 or 1. So the degree we have to take off highest order derivative. So it will be equal to 1, right? So this is the basic introduction of partial differential equations, and let's move further and let's see some other concepts to enhance our knowledge, right? So let's see something called standard notations in derivatives in partial differential equations, right? Let's see. So standard notations, let's see what is meant by it. So suppose if z is a function of x comma y, means it is dependent upon x and y. So in that case, del z by del x is called p. Del z by del x is called p. Suppose z is equal to x square plus y square. So del z by del x will be equal to p is equal to 2x. Correct? Simple. And suppose del z, and let me write it next line, right? In next line. So del y, it is called q. So del z by del y is called 2y, right? It is equal to 2y, right? Simple. Basically x is constant with respect to y, so it is equal to q, right? Correct? Okay. Now there's something called del 2 z by del x square, which is equal to r, and del 2 z by del y square, which is equal to t, right? And I should write it in sequence. So del 2 z by del x del y is called s, and del 2 z by del y square is called t, right? Simple. So basically take the second times derivative of this quantity. So basically it is equal to del p by del x, and this is equal to del q by del y. Correct? Okay. So understood this? Simple. Okay. So basically what we are going to do is we will apply these notations frequently in next problems. So we should remember them. Okay. These are some of the standard notations basically, right? So it is not necessary to remember them, but in questions it is important, right? So it is just a notation, if I say in simple words. So del z by del x is called p, del z by del y is called q, del 2z by del x square is called r, and it is also equal to del p by del x, right? Simple. Okay. So this is how we write such expressions, right? Okay. So let's move further. Now let's see how we formation of partial differential equations. So let's see how we form partial differential equations. So well, there are two methods in this case, by elimination of, let me write it like this, elimination of first arbitrary constants and second arbitrary functions, and we'll see them, right? So let me explain it. Suppose first of all, let's see arbitrary functions, I mean arbitrary elimination by arbitrary constant, right? So suppose there's a function f of x y z a b is equal to 0. We have such kind of function, so where x y are independent variables, z is a dependent variable, a and b are constants, right? So a and b are constants, a b are constants, right? You should remember this. Okay. So in this case, when you differentiate this expression, suppose with respect to x, right? So when you will differentiate it with respect to x, then you will get del f by del x plus del f by del z dot del z by del x is equal to 0. It is with respect to x. Now I know that there must be a question that why I did this. Well, I recently made a video regarding this, but if you don't know that video, if you did not watch that, then in that case I can explain you that z is a function of x itself, of course x and y. So if z is also a function of x, so it means that we have to apply chain rule in this case. Simple, understood? So that is why we had this expression, then we had this expression, right? Basically, if you have zx plus y is equal to 0, if you take its derivative, then it will be del f by del x plus del f by del z plus, I mean, into del z by del x. Simple. So when you take its derivative, this is z, this is z. So you can just write it like when you take its derivative with respect to x, you get z, z plus del f by del z, it will be equal to x into the quantity del z by del x, which is equal to, again, x is equal to 0. Correct? Simple, right? Correct or not? Correct? Yeah. Sorry, del z by del x. It's right. Sorry. Okay. So understood this thing? Right. And yeah, you can do it like that also, like zx derivative, it is equal to, of course, you can take its derivative easily. It will be z plus x del z by del x itself. Very easy, right? Simple. Correct or not? Correct? Yeah. So this is the expression z plus x del z by del x is equal to 0, and we get from this expression itself, right? If you don't understood this part, then you can watch my that video in that I've explained it in bit detail. Of course, it's one short, so I could explain this much only. And if you want to learn more, it's just a 10 minutes video. You can watch that. Okay, I will put its link in description, right? So basically, this is the concept. Okay, and now let's differentiate it with respect to y, right? So let's see what we get then. So it will be del f by del y plus del f by del z dot del z by del y is equal to 0. It is with respect to y, correct? Understood? So it was with respect to x and it was with respect to y, right? So clear? Again, z was a function of x and y both, so that is why we had this expression also. Simple? Okay. So, but I told this much. How can we do actually? I mean that we solved this much part. So what else we need to do? Well, we need to just eliminate a and b from this. And notice one thing, that this is equal to q, and this is equal to this is equal to p, right? Correct. Okay. So when you eliminate a and b, you will get the equation, you will get the expression form of f of x, y, z and p and q, probably a different function, suppose phi, right? And this is the differential equation, which is required partial differential equation, right? Simple. Okay. So now let's do a problem to understand this concept, but we need to know one thing, that the number of arbitrary constant, if they are equal to the number of independent variable, then in that case it is a first order differential equation. Of course, in this case a and b, there were two variables, two arbitrary constants, I mean, and there were two independent variables. So in this we got p and this expression in terms of p and q. So if we got in terms of p and q, so p is also first order and q is also first order, right? Okay, so of course this is a first order differential equation. But if number of arbitrary constants is like greater than number of independent variable, then it is second order or greater than second order, right? Okay, so this was the basic introduction. Let's solve a problem. So let's see a simple example, that z is equal to ax plus by plus ab. It is a very simple example. So in this case, del z by del x, what it will be equal to? It will be equal to a, and del z by del y, it will be equal to y. It will be equal to b. Correct, right? So just substitute this over here. You get z is equal to x del z by del x plus y del z by del y del y plus del x, I mean del z del x dot del z by del y, right? So it's a first order partial differential equation, right? Very simple, very easy. Let's see another problem also, and it is a bit typical, so let's understand it, right? So x square by a square plus y square by b square plus z square by c square is equal to 1, right? So how we are going to solve this kind of problem? Well, it's very simple. So let's differentiate it with respect to x. Differentiate with respect to x. Let's do this and let's see what we get. So we get 2x by a square plus it will be 0 plus 2z by c square d del z by del x is equal to 0. Simple, okay. And of course 2 and 2 will get cancelled, okay. So we get x square by a square and this by c square. Simple, understandable, okay. So now with respect to y, we will get similarly y by b square plus z by c square del z by del y, right? This expression. Now we need to use this expression and this expression to do something, right? But we know that here we have three variables, three arbitrary constant. I mean we have three arbitrary constants. So it means that it is greater than the number of independent variables, that is 2. Hence it will be second order or greater than that. So of course we need to differentiate one more time. So let's differentiate this expression with respect to x again. So we get in that case it is equal to 1 upon a square plus 1 upon c square. Now when we differentiate it, what will we get? We'll get del z by del x whole square plus z del 2z by del x square is equal to 0. Wait, let me tell you. Z del z by del x, del by del x. We are applying this operator on this given variable or a function. So we'll apply the product rule in this case, right? So we'll get del z by del x into the derivative of this quantity. It will be del z by del x, of course, whole square plus z times the derivative of this expression. We get del 2z by del x square, and this is what is required. Correct? Simple. Okay, right? So when you solve this expression, you get c square by a square plus this expression is equal to 0. And when you solve this expression, you will get what? You will get c square by a square plus z by x del z by del x is equal to 0. Correct? We got this expression. Simply we just divided by x both sides and we multiplied c square both sides, right? So of course we did not need this expression actually, but still we solved it. So from this we can say that this expression c square by a square is equal to negative z by x del z by del x, right? Now we can substitute this expression over here. So we get negative this quantity del z by del x, we get this expression plus del z by del x whole square plus z del 2z by del x square is equal to 0. And this is the required partial differential equation. It is of second order actually, right? And what is its degree? It is the degree is 1, right? Simple. Okay, so now we solved the problem with respect to first order and second order. So of course that is what is required in this. Okay, so now let's move to formation of partial differential equation by elimination of arbitrary functions. Let's see that. So by elimination of arbitrary functions, right? So let's assume a function, let's assume that z is equal to a function of u, where u itself is a function of x, y and z, right? So where f of u is an arbitrary function of u, and use this expression. So when you solve for del z by del x, you will get del f by del x plus del f by del u dot del u by del z dot del z by del x. Why? Because again here it's the chain rule simply, right? Why? Since this is a function of u, so with respect to u itself is a function of z, so that's why we have a z, and z itself is a function of x, so we went to that level, basically like that. Okay, so this is the chain rule. Basically you can watch my that video, that 10-minute video, in that you will understand it better, right? I've explained that. And similarly, del z by del y, it will be equal to del f by del y plus del f by del u plus del u by del z dot sorry, it will be a dot over here, del z by del y, right? Simple, this expression. And from this you have to eliminate arbitrary function, which we will understand in a few seconds when we see example, right? Okay, so one thing to be noted over here is that order is equal to the number of arbitrary function eliminated, right? Correct. Okay, and one more thing I forgot over here, it will be del u dot del u by del x, sorry, it will be del f by del u dot del u by del x, sorry, this I forgot this del y. Okay, yeah, this one, because again we have to apply chain rule. Okay, so we're right, simple, understandable, right? Okay, so you can watch my that video in that I've explained it clearly. Okay, so let's move further. So let's see a question that z is equal to a function of x square minus y square. So this is a function which we need to means over here basically u is equal to x square minus y square basically, right? So in this we have to form a partial differential equation. So let's see how we'll form using, so where function, where f is the function of u with respect to, where f is an arbitrary function, is an arbitrary function of u, right? Basically, right? So we get z is equal to f of u. So we get del z by del x is equal to the quantity del f by del u dot del u by del x plus the quantity del f by del u dot del u by del z dot del z by del x, right? Now notice that in this case del u by del z is 0. Why? Because you can clearly see from here, because del u by del z will become 0 since there is no z in that case. So this expression is equal to 0 in this case, right? So we get del z by del x is equal to del f. Now del f by del f by del u dot del u by del x, it's 2x. Simple. Okay. Now similarly, del z by del y, you can apply that formula in that you will get del u by del z is again 0. This expression is already gone. So del f by del u dot negative 2y. Simple. You can solve it on your own. Now let's just divide these two expressions. We get del z by del x divided by the quantity del z by del y is equal to negative x by y. So this is p, this is q. So we get p by q is equal to negative x by y. Correct? Simple. Okay. So this is how you solve such kind of expressions. And yeah, there's one more problem which I had discussed before, like z is equal to f of x plus it plus g of x minus it. You can check out that video. In that I discussed this problem. So there are two arbitrary functions, so it will be a partial differential equation of second order, right? Because we have to eliminate two arbitrary functions in this case, f and g. There are two arbitrary functions of these two variables, of these two means x plus it and x minus it, right? Okay, so let's move further. Now let's understand solution, solution of partial differential equation. So let's see that how we solve a partial differential equation, and of course we have to understand many things in this. So we'll go in a sequential order. First we'll study Lagrange method. Basically I will tell, okay, don't worry. Okay. So first of all, let's see that how do we solve a first order partial differential equation. But first of all, let's see its form. We have seen it is x, y, z, p and q, right? This is a this is a general form of a first ordered partial differential equation. Simple. Okay. So now let's understand. So it is just the reverse of that, or the yeah, that is just the reverse. Let me explain. So if you are solving for you are finding its solution, so its solution will be f of x y z, maybe some phi, you can say a comma b is equal to 0, right? Where you just replace p and q with some constants which you need to find first. We will see it. So x, y, and z are the variables. X, y is the independent variable. Z is the dependent variable, and b are the constants. Simple. Okay. So this is how you solve it. Basically, we will understand this in some time. This is just some theory which I'm telling. Okay. So yeah. Okay, that's it. And the solution of print form. What is the particular integral solution? Pi. Well, in this reference, it's something different. So basically, when you substitute some value for x and y and you get some answer in that case, so in that result is called particular solution basically, but you don't need to worry much about that. Okay? Basically, when you are set to evaluate at when x is equal to 1 and y is equal to 2, that case, right? Basically that yeah, phenomena. And general solution, basically general solution is like that. Okay. So specified function uv, yeah. So that is not much required, that I will tell in later part. Okay. So let's see a problem to understand this concept. So we are given that proof if u1 and u2 are the solution of the quantity del 2u by del x square plus del 2u by del y square plus del 2u by del z square is equal to a del 2u square u by del t square plus b del u by del t, then C1 U1 plus C2 U2 is also a solution. Well, let's see it. Basically, it is the linear combination of these two functions, these two solutions, U1 and U2, right? So first of all, let's substitute U1. You get del 2 U1 by del x square plus del 2 U1 del y square del 2 U1 del z square is equal to a del 2 U1 del t square plus b del u1 by del t, correct? Simple. And you substitute u, del 2 u2 by del x square plus del 2 u2 del y square plus del 2 u2 by del z square plus a del 2 u2 by del t square plus, I have written plus over here, it is equal, plus b del u2 by del t, correct? Okay. Now basically multiply both sides by c1. In this case, c1, 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 right? Correct. Here c2, 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 correct, right? Now there's no harm if I bring c1 over here, correct? And similarly I can do with all the expressions, and in this also I can do like this, and I can simply add these two expressions. So will it make any sense? Well, we have to prove this only, so we can't do like this. Okay, so that is where we lose marks. I say many people ask that this is correct, then why it was said wrong? Basically you need to prove that expression. So how can you say that yeah, I can bring c1 over here so it's correct? No, it's wrong. Okay, so now let's assume that this is the solution of the given differential equation. So we get del 2 of the quantity u1 c1 u1 plus c2 u2 by the quantity del x square plus del 2 c1 u1 plus c2. Let me solve this one first, so you will understand the rest on your own, right? So basically you just expand this expression, so you get del 2 c1 u1 divided by the quantity, this expression, plus the quantity del 2 c2 u2 del x square. Now c1 and c2 is constant, so you can bring them out, yeah, like this. So it means that you just multiply over here, and when you add, you will get this expression itself. So it means this is equal to this quantity, right? Hence the linear combination is also the solution of the given differential equation of these two, which has these two solutions, u1 and u2, right? So of course, if there are n solutions, the n linear combination of these variables will be the solution of this differential equation, right? Correct? The linear combination of these solutions, right? Okay. So understood, right? Okay. So now let's see Lagrange's linear equation, how we solve them. Let's see that. So linear partial differential equation of first order, which is often referred to as Lagrange's linear equation, right? We will see it, don't worry. Okay, linear equation, linear equation, right? Okay. So before that, we should know that what is meant by a linear differential equation. This is the linear differential equation. So basically, if dependent variable and its differential coefficient, right, occur only in uh, in the first degree, and not multiplied together. Yeah, they should not be multiplied together and not multiplied together, right? Okay, correct. So it's called a linear differential equation. And what is partial linear differential equation? Well, if dependent variable z and its derivative remember this, if the dependent variable z and its derivative occur only uh, r of basically r of degree 1 and product of z and its derivative not involved. Basically this definition only, but here we have specified a variable z, that's it. Okay. And what is a homogeneous partial differential equation, right? Okay. So if in a partial differential equation each term contains what I'm writing contains the dependent variable right, or its derivative, then such PDE or partial differential equations is called a homogeneous partial differential equation, whatever you want to say. Okay. So these are some of the definitions which you won't be tackling, I know it. So most of the problems which you will see, it will just based on like the mixture of these kind of things. So you don't need to worry much about the definitions. But of course, for conceptual purpose, you should know the definitions, right? So what is the linear differential equation? What is the partial differential equation? What is the homogeneous partial differential equations, right? So what is the this each term contains the dependent variable or its derivative, then it is called this. Okay, simple. Dependent variable is necessary in this case. And what is linear partial differential equation of first order? Now that's something interesting. Let's see it. So of first order, first order. Now if it's of first order, then it is of the form, I mean a partial differential equation of first order is of the form this P and Q, right? PQ. So it means that in this also P and Q will play a great role, a significant role, right? Okay, so let's define it. So this is the first order, and so in this case, P and Q must only appear in derivatives, and they must not be multiplied together, right? Correct. And of course, the basic definition of linear differential equation, it must follow the partial linear differential equation, right? That z and its derivative should not be in product and something like that. Okay, and of course, P and Q must not be in product, right? Correct. Yeah. So now let's see something called quasi linear partial differential equation, right? Let's see what is it. Okay, so basically it is a non-linear partial differential equation, if I explain it in simple words, right? So if degree of highest ordered derivative is one and no product of partial derivatives of higher are present order are present, correct? Okay, so basically you don't need to worry much about the definition. Basically it is something called basically it is a non-linear partial differential equation, right? If I explain it right, of course there are some differences, but we don't need to worry right now. Okay, when we will solve problem we will understand it, right? Don't worry. Okay, so these are some of the definitions. Let me see that is there any definition which is left. Probably no. So let's move to the next part. Now let's see something called Lagrange's linear equation. Let's see. Okay, so general form of a quasi-linear partial differential equation which we studied, it is of the form P x y z P, where P is equal to not capital P. This P, capital P is a function, and P is equal to del z by del x, right? Okay, plus Q of x y z, Q is equal to R of x y and z, correct? Okay, so where P, Q and R is linear in z, so if P, Q and R is linear in z, then equation becomes linear partial differential equation, right? And of course notice one thing, that in this case P and Q, it must be independent of z. Why? Because of course if they will be dependent upon z, then in that case it will be z times P, right? Z times P. So in that case, if it is z times P, then so basically let me reframe it. If P and Q are independent of z and R is linear in z, then the equation becomes a linear partial differential equation. How? Because again, if it is dependent upon z, then it will become z times P or z times Q. So of course, then it will be non-linear partial differential equations. Is a product of the dependent variable and its derivative must not be involved, right? So hence it must be independent of z, this P and Q, and R must be linear in z, right? Of course, R can be a linear function in z, right? Simple. Okay. So, right. Now let's see how we solve such kind of equations. Let's see. Okay. So such equations is obtained by eliminating arbitrary function. Let's assume phi. For now, let's assume it, right? Then we'll see it using examples in a better way, right? From phi of u comma v is equal to 0, right? where u and v, they are the known functions, they are the known function of x, y, and z, right? So basically, we have to define an arbitrary function which is the function of u comma v, where u and v are itself the function of x comma y comma z, right? So don't worry about it. We will see in examples that yeah, that is not even required. It is only required for derivative, and of course, you need to know a function, an arbitrary function, to solve this equation. Of course, we form a differential equation using the elimination of arbitrary function. So of course, we'll solve it also using that. Okay, that is the basic concept. Don't worry about it. Now let's see how we solve that kind of equation. So we know something called Lagrange's auxiliary equations. So of course that is Lagrange linear equation, and now we are going to solve Lagrange auxiliary equation. That is, we had phi of u comma v is equal to 0. We had this expression, remember, from that. Okay, so we are going to solve now Lagrange linear equation using something called Lagrange's auxiliary equation, right? So let's differentiate it with respect to x and y. So when you differentiate it with respect to y, first of all, let's do it with respect to x. You get del phi by del u times the quantity del u by del x plus del u by del z times the quantity. Basically, if you don't understand this, let me just write it. So del phi by del u dot del u by del x plus del phi by del u dot del u by del z dot del z by del x is equal to 0, right? Correct? But remember, this is for this expression for u. We have to check for y, for v also, since it's the function of u and v. So del phi by del v dot del v by del x plus del phi by del v dot del v by del z dot del z by del x, and it must be equal to 0. Why? Because we had it is equal to 0. Simple, right? So this is just a chain rule and some sort of product rule which we applied, but you don't need to worry about it. You can understand it using chain rule easily, right? Since phi was a function of u, so we had done chain rule over here, and now use itself is a function of z, so that is why we have del z by del x, right? Let me see that is it correct or not. So yeah, it is correct. And yeah, instead of del z by del x, you can write simply p, and over here, sorry, it will be, yeah, over here also you can write it p, right? Simple. Okay, now with respect to this, with respect to x, we differentiated, and when we differentiate with respect to y, we get del by u, del u by del y plus del phi by del u dot del u by del z dot del z by del y plus del phi by del v dot del v by del x plus del phi by del v dot del v by del z dot del z by del y is equal to 0, and it is with respect to y, right? And of course this is equal to q. Of course del z by del y was equal to q, so let's substitute that. Okay, so this is how you basically, this is the expression when you differentiate this expression. Okay, so let me check, is it correct? Yeah, del u, this is del u, remember I had written it like v. Okay, yeah, that is correct. Yeah, this expression, sorry, this will be y, forgive me. Yeah, it will be y, sorry. Okay, so this, okay, so from this you have to eliminate pi. Remember in the elimination what we had done, elimination of arbitrary function, we have eliminated a function. So here this was the arbitrary function, so we will eliminate phi in this case. So we have to eliminate in this del phi by del u and del phi by del v, right? So when you eliminate this, what you will get is that when you solve it, you will get this expression. Of course, you can solve it on your own. This is just an equation. You can assume basically you can assume this as variable and this as variable, this one, and then you can solve for x. Maybe you name it as t1 and this as t2. You solve for t1 and t2, and when you solve them, you will get this expression. When you eliminate these two expressions, what you will get is that um, del u by del y dot del v by del z minus del u by del z dot del v by del u del y, correct? Yeah, times p plus, basically I've eliminated this and this, and after eliminating them I'm getting this equation, right? So we get del u by del z dot of course I'm not solving this equation, I'm not eliminating this, you can do it on your own because it will take unnecessary time, which you can do easily, right? Minus del u by del x dot del v by del z q is equal to del u by del x dot del v by del y minus del u by del y dot del v by del x, whatever, right? This is the expression. Now this is something, this is p, this is q, and this is r. So p p q q and is equal to r. That was a Lagrange's linear equation, right? Remember, just few seconds ago we had just, I mean few minutes ago we discussed that. Okay, that is what we need to remember right now. Now how to determine u and v? Well, now that's something interesting. Let's see that. Okay, now just remember this expression if you can, or just note it down, so if it is required we can see it in next part, right? So let's see it further. Now how to determine u and v? Well, now that's an interesting question. So there's a method to solve this. Let's see it. Let u is equal to a and v is equal to b, right? Where a and b are constant. So of course we had taken just randomly u and v, so that is why we assumed it as constant, because a constant, if it is a constant, then it is very easy to solve because its derivative will always equal to 0. So that is why it is very much easy to solve using a constant. So why not? Okay. So we had this expression that well, you know one thing, that du is equal to del u by del x into dx plus del u by del y dy plus del u by del z into dz, right? This is the complete derivative basically. Okay, so basically this is how you do it. And similarly you will have dv is equal to I mean del v by del x dx plus del v by del y dy plus del v by del z dz, right? This will be also equal to 0 and this will also be equal to 0, right? Okay, now when you cross multiply these expression, so you will get dx by del u by del y dot del v by del z minus del u by del z dot del v by del y, right? Basically you must have studied cross multiplication method in solving a linear equation. So basically that's what I'm doing over here. And just this is solving for dx dy dz, right? Is equal to dy by del u by del z dot del v by del x minus del u by del x dot del v by del z is equal to dz by del u by del x dot del v by del u minus the quantity del u by del y dot del v by del x. Now just rewind this video and go to the section where I had written P, Q and R. This was P, this was Q and this was R. If you have written in notes, then good. If you have not, then just rewind this video. You will see that this was P, this was Q and this was R, right? Okay. So dx by P is equal to dy by Q is equal to dz by R. And it is now very easy to solve such kind of equation, right? Simple. So understood that what we are going to do. Okay, so yeah, from this we get this expression, right? So we got this. Okay, so what's next? Well, let's see a problem to understand this. Okay, so let's solve this question that pz minus qz is equal to z square plus x plus y whole square. Simple. Okay, so we can write it like p minus q, or basically you can write over here that p is equal to z and q is equal to negative z, and r is equal to z square plus x plus y whole square. Correct? Okay, simple. So we have dx by what quantity? Z is equal to dy by negative z. Dy by negative z is equal to dz by z square plus x plus y whole square. Correct? Now just equate these two expressions. So dx is equal to dy negative z and z gets cancelled, so it is equal to negative. So we have del dz plus dy is equal to 0. Just integrate this expression, so you will get x plus y is equal to some constant a. Now notice this expression that you have dx by z is equal to dz by z square plus a constant a. So you have dx is equal to z by z square plus a square, dz multiply by both sides 2. Now just integrate this expression. What you will get? 2x is equal to the natural log of mod of z square plus a square plus another constant b, right? Okay. So you got this expression, you got this expression, right? So instead of a, you can substitute that. And so we can get from here that we can say, we can solve for b from there. So we get the expression phi. Now, of course, why I'm writing phi? We have got the result. Then why I'm writing phi? Because a and b are constants. Remember, a and b are constants. So b is equal to natural log of z square plus a square, that is x plus a, minus 2x. Now we assume that the solution was phi of u comma b, but u comma b was a comma b. A comma b is equal to 0. So the solution is this expression x plus a, x plus y is equal to a comma the natural log of z square plus a square plus, x plus y whole square minus 2x is equal to 0. Correct? Now understood, this is the solution of the given equation. Now phi is an arbitrary function of u and v or a and b or this expression. So you can define any function, it will satisfy this. And that's the beauty of partial differential equation. Ordinary one, you did not got many solutions, but over here you can have infinite solutions also. Simple, right? Okay. Now let's see how we solve non-linear partial differential equation of first order. And we are going to see standard forms, right? Standard forms. Okay, like the forms like so basically, let's see a partial differential equation which involves first order partial differential p and q. That is just basic definition, right? Of course, you know what is meant by linear partial differential. A non-linear partial differential is the one which is not a linear partial differential equation, right? Simple. And that is how you answer in your vibe also, right? We all answer like that. A non-linear partial differential equation is a partial differential equation which is not linear, right? Okay, you leave that. So why I'm writing solution? Okay, so what are the standard equations? The first one is f of p comma q is equal to 0, right? And the second one is z is equal to px plus qy plus a function of p comma q. Third one, f of z comma p comma q is equal to 0. And fourth one is f1 x comma p is equal to f2 y comma p, right? Okay, don't worry. So these are some of the standard forms which we are going to solve, right? So we are not going to solve it like for a general case, but for these standard forms. And we are going to see Charpit method in maybe in the next part of this video, which I have recorded in NIT, because probably there's very less time now. So that is why I will stop this lecture, means this one, after maybe I complete this part, okay, and then I will record the second part in NIT itself, right? And then I will club them together and I will upload it, okay? So don't need to worry, I will make 2 parts. No, not like that, okay? So let's start with this. So let's see the first form, f of p comma q is equal to 0. So in that case, solution is z is equal to ax plus by plus c, right? Where now here there are three variables, three arbitrary variables. So is it wrong? No. Where f of a comma b is equal to 0. So from this you will get an expression for means a relation between a and b, right? So instead of three arbitrary constants, you will have only two arbitrary constants, right? Okay. So right, okay. So instead of this, if you solve, you will get like b is equal to some phi of a, right? If you solve this expression, so instead of this you can write phi of a, right? Simple. Okay. So let's see. Let's see a question. Suppose root p plus root q is equal to 1. Very simple question. Solution z is equal to ax plus by plus c, right? Now we have to substitute a and b, so you get root a plus root b is equal to 1. Correct? So you get b is equal to 1 minus root a whole square. You get a plus 1 minus 2 root a, right? Substituted back, you get z is equal to ax plus a plus 1 minus 2 root a y plus c, and that is the answer, right? Simple. Okay. Now let's see a question which is like reducible to this form. Let's see that one also. Now let's see this question. It is like reducible to this form. Let's see it. Y minus x into the quantity qy minus px is equal to p minus q, right? Whole square. So of course you saw y and x in this, so you thought no, it is not of this form, but actually it can be converted. Let's see how, right? So basically there's some substitution which you have to do in this. X plus capital Y is equal to, or I mean small x plus y is equal to capital X, and xy is equal to capital Y. Let's do the substitution for now, right? So when you do this, you will get del z by del x is equal to del z by del capital X dot del capital X by x plus del yeah, that's it. Why I'm writing further, right? So yeah, plus del z by del y capital Y dot capital Y by capital small x, right? Since y is also a function of this, so that is why we have to do this also. So basically it turns out to be equal to what? Del z by del capital X plus y del z by del capital Y, right? Okay. Similarly, del z by del y is equal to del z by del capital X dot del capital X del y plus del z by del capital Y dot del capital Y by del y. Simple. And this is equal to what? This is equal to, well, simple. It is equal to, we can solve it, right? So you will get del z by del capital X plus x del z by del y. Simple. Okay. Now, what is the value of y minus x in this case? Well, we will solve all this. So what is it equal to? It is equal to p and it is equal to q, right? Of course, del z by del x is equal to p and is equal to q, right? Let's substitute this value. So y minus x as it is, right? Now q times y means y times this expression. So y del z by del capital X plus xy del z by del y, right? This is qy minus x times x del z by del x plus xy del z by del y is equal to the quantity is equal to p minus q. P minus q, it is equal to y minus x whole square into the quantity del z by this quantity, basically del z by del y, capital Y whole square, right? Okay. So this expression gets cancelled. So you have y minus x whole square. Just do a little bit of maths over here. You will see yourself is equal to y minus x whole square del z by del y whole square. This and this gets cancelled, right? Okay. Now this is suppose P1 and this is Q1, right? Let's assume it. So P1 is equal to Q1 whole square. This is again of the form f of P1 comma Q1. That's it, right? Or P comma Q. So again you get the answer as Z is equal to A capital X plus B capital Y plus C, right? Where f of A comma B is equal to 0. So we get sorry, yeah, whatever. So you substitute the value A is equal to B square, right? So you can say B is equal to root A, maybe, right? So Z is equal to root, I mean A. What is the value of X? Capital X? Well, from these two, you can solve for the value of capital X, right? Whatever you get the value plus root A, whatever you get the value of capital Y from this, I mean, capital X is simply X plus Y, what I'm saying. Yeah. And capital Y is simply XY, right? XY, right? Plus C, right? Okay. Simple. So this is the answer, required answer, okay? Right, so it's correct also. Yeah, maybe. Okay. So x is equal to x plus y and y is equal to xy. Yeah, correct. Okay. So these are you solve the reducible problems, right? In this form. Now let's see the second form. Okay. Now the second form is z is equal to px plus qy plus a function of p comma q. Okay. Now the solution in this case is z is equal to ax plus by plus f of a comma b. Correct. Now let's see a question. Right. Okay. So it is very simple now. Right. Z is equal to ax plus qy plus a plus by plus root 1 plus a square plus b square. Simple. That's the answer. This was the function. We substitute a and b in place of it. We got the answer. Right. Now let's see a reducible problem. Reducible to this form. Let's see that also. Okay. So it's a simple problem. Just you need to do some sort of manipulations. Of course, the solution was ax plus by plus a function of a comma b is equal to z, right? Okay. So let's see the question. It says that 4xyz is equal to pq plus 2px square y plus 2qxy square. Simple? Not simple. We will first of all need to solve this expression. So we see x square, we see y square. So we get an idea that yeah, we can substitute x square as capital X and small y square as capital Y, right? And of course we can see that yeah, it is not of this form, so we can make it, right? Okay. So let's say x square is equal to capital X and y square is equal to capital Y, right? Okay. Of course, whatever substitution you have to make, it just comes with practice, right? There's no remedy for that, I will tell you that these are the substitutions which you need to remember. No, that comes with practice, right? I can tell some of the problems in and the problem there might be some other substitution, and there is a possibility that that substitution I also don't know that what we can substitute. So it can only come with practice, right? I can't tell all the substitutions, right? It depends on the problem itself, right? So there might be a problem which has a something truly new substitution in that case, so that no one knows. It will take time to understand that one. Okay. So that is something which you should know. So from this you will get del z by del x again is equal to del z by del capital X dot del capital X by del x. Of course, by del uh, capital Y by del x is equal to 0. So we don't need to worry about that. Del z by del capital X, this it will become 2x, and del z by del y is del z by del capital Y dot del y by del y is equal to del z by del capital Y dot 2x, I mean 2y, right? Just substitute it over here, you will get the answer. Okay, let's see it. So it will be equal to, well, let's see it. Okay, so this is the expression which we are getting. Now we can say it as 4xyz is equal to the expression 4xy, of course, p and q, 4xy del z by del x del z by del y plus this expression 4x cube y 4x cube y del z by del x plus 4x y 4xy cube del z by del y, right? Simple. Okay, xy gets cancelled, it becomes like this, simple. Okay, and now we have 4z is equal to, and of course 4 also gets cancelled, right? So we get z is equal to what? It is equal to x square is capital X del z by del x plus this is capital Y del z by del capital Y plus del z by del x dot del z by del y, right? Now we can say it as small p1, this is small p2, q2, q1. Okay, z is equal to x p1 plus y p q1 plus p1 q1, right? Now just substitute it over here, you will get z is equal to uh, ax plus by plus ab, right? A x square plus by square plus ab, right? Simple. That is the answer. Okay, yeah, correct. So let's see the second form now. It is, yeah, we have the second form. Now let's solve that. Okay, so this is the second part and I'm recording this in NIT Durgapur. So let's start the lecture. So we were on the third equation, that f of z comma p comma q is equal to 0, right? So to solve such kind of expressions, what we do? Well, in this case, we assume that let z is an arbitrary function of x plus ay, okay? Or you can say it is equal to phi of u, an arbitrary function of u, where u is equal to x plus ay, correct? Okay, fine, okay. So if you calculate del z by del x in this case, what you will get? Well, you will get del phi by del u into del u by del x, correct? Of course, if z is a function of phi of u, so of course del z by del x is equal to del phi by del u dot del u by del x, chain rule, simple, right? Okay, so what is del u by del x? Well, del u by del x is equal to 1, correct? Simple, it is u is equal to x plus ay. So when you differentiate it with respect to x, you will get 1, right? So it is equal to del phi by del u. Now the interesting thing over here is that you can say that z is equal to phi of u, correct? So you can say that dz, the proper integral dz by du is equal to d phi by du, correct? And of course they both are equal. Del phi by del u, since del phi by del u, and since phi is a function of one variable only, phi is a function of u only, so we can say that del phi by del u is equal to d phi by du, since phi is a function of a single variable. So when you take its derivative, it will be equal to d phi by du. So it is equal to d phi by du. It is equal to dz by du, right? So we have p is equal to dz by du, correct? So we should write this expression over here. P is equal to dz by du, correct? Simple. Understood or not? Since when we have a function in a single variable, so in that case we get a proper differential equation or proper derivative, right? Not partial, right? Since phi is a function of one variable only, u, right? Okay, right. And over here z is also a function of u only, because we assume z is equal to phi of u. Okay. Understood? Okay. So we have this expression. Now let's see for q what we'll get. Let's see. So let's solve for del z by del y. So over here also you will get this only, right? Okay. So del z by del phi, it can be written as del phi by del u dot del u by del y. What is del u by del y? It is equal to a, right? Okay. A d del phi by del u, right? What is del phi by del u? It is equal to d phi by du, and d phi by du was equal to p, which was equal to dz by du, correct? So it is equal to a dz by du, correct? Understood, right? So we have q is equal to a dz by du. So this expression is equivalent to saying that f of z comma f of z comma p is equal to dz by du, dz by du comma a dz by du, a dz by du, right, is equal to 0. So now let's see a problem to understand this. Okay, so let's see. So let's see the question. The question states that z square times p square plus q square plus 1 is equal to a square, right? Okay. So basically it is function of z, p and q only, right? So in place of p you can substitute dz by du, and in place of q you can substitute dz by a dz by this quantity. So you have z square times the quantity dz by du whole square plus a square dz by du whole square plus 1 is equal to a square, right? This expression correct. So now what you can do, is that you can bring that expression over there. So you get dz by du whole square. You can take common. You will have 1 plus over here. Let's assume it as b, right? Because of course we have used the variable, the constant as a over here. So let's name, instead of a over here, let's name it b. Okay, fine. Okay, 1 plus b square, that one will go there, so it will be equal to a square by z square minus 1. Understood or not? Right? Basically I brought that z square in the denominator, and then I had expression, this expression I mean dz by du whole square plus b square dz by du whole square plus 1 is equal to a square by z. So I brought this one term to the RHS, so it became -1. That is what I would. Correct? Okay. So from this you can say that dz by du whole square is equal to a square minus z square by z square into the quantity 1 upon 1 plus b square, but it does not matter because 1 plus b square is a constant, right? So it's simple. You can take the square root both sides and then you can integrate it. You will get the answer, right? Understood? Simple, right? So you know how to solve this kind of differential equation. It is ODE, right? You can watch my lecture on ODE. So if you have problem with this kind of problems, right? So in this you can solve, and you know the value of u is equal to x plus ay, right? So substitute it, you will get the answer, right? So let's move to the fourth form. So the fourth form is f of x comma p, f of x comma p, f1 a function is equal to f2 of y comma q, right? Okay. So in this what we do is that we assume f1 of x comma p is equal to f2 of y comma q and set it equal to a, where a is a constant, right? A is a constant in this case, okay, right? So what we do next is that we assume let p is some f1 of x and q is some f2 of y, right? Okay, I will tell everything, just wait. So we know that dz, when you will see the question you will understand, okay? So don't worry why I am doing this, okay? So dz, the complete derivative of z can be written as del z by del x dot dx plus del z by del y dot dy, right? So what is del z by del x? It is equal to f1 of x dx plus f2 of y dy. This dz, just integrate this, you will get your answer, right? So that is why I assume p as the function of x and q as the function of y, because it will be then easy to integrate this expression. So let's see it to understand it better, right? Let's see a problem in this, okay? So let's see the question. The question states that yp is equal to 2yx plus log of q. So what was the expression? It was f1 of x comma p is equal to f2 of y comma q, right? So this is the expression. So it is of this form that f of x comma p is equal to f2 of y comma q, right? So let's see, is it of this form? Well, we have to make it because it is still not in that form. So we can see a p over here, which should not be over here, right? So yp, we can bring this expression over here, minus 2yx is equal to log of q, correct? Okay, basically we have to make it of this form. So we want x and p to be together and y and q to be together, right? So that is why we are rearranging it. You can take y as common. P minus 2x is equal to log of q. So from this you can say that p minus 2x is equal to log of q by the expression y, right? Okay. Now it is of this form that f of x comma p is equal to f2 of y comma q, right? So now let's see how we'll solve it. Well, so our of f1 of x comma p, we assumed it as a constant. So we will get from this, we are going to get p minus 2x. P minus 2x is equal to a. So we get p is equal to 2x plus a, right? Which is f1 of x. Now you know that why I said there f1 of x only, not f1 of x comma y, because of course it is a function of x and p only. So when you will rearrange this, you will get only a function in x, p as a function only in x, not in y, right? Uh, do you understand it? Not similar is the case over here. Suppose it is only a function in x and p, so when you will set it equal to some constant, and when you solve it, you will get the relation between p and x only. No y will be involved in that, right? Similarly, we can say f2 of what was it, y comma q is equal to a. We set both as a, which implies it is equal to log q by y is equal to a. So we can say that q is equal to e to the power ay, correct? Which is equal to f2 of y, right? Again, when you separate y and p in this and set it equal to a, you will get only a relation between q and y. No x will be involved in that, right? Okay. So dz is equal to f1 dx plus f2 dy, just from that expression. So you have 2x plus a dx plus e to the power ay dy plus some constant when you integrate this, and it is equal to z. That is the answer, right? Understood? Now it is very simple to integrate. If you want, I can do that also. X square plus ax plus e to the power ay by a plus a constant, right? That is the answer. Okay. Yeah, correct. Yeah, instead of c, you can assume b, whatever you want to assume, right? So yeah, that's it. So now let's move to Charpit method. What is it? Let's see that. Now let's see Charpit method. Charpit's method. So it is basically a general method to solve a non-linear partial differential equation. So let's see it. Okay. So it is a general method to solve. Yeah. Let me write some point. General method to solve non-linear first order partial differential equation, right? Okay. And and in this we use this formula that dz is equal to del z by del y del x dx plus del z by del y dy, right? Okay, but what does this expression tell? Well, it tells a total gradient along x-axis and y-axis. So that is why we have a del z by del x, and this we have del z by del y, correct? Okay. So now we can integrate this expression to get our answer, like we did in the fourth method, similar to that, right? So to get result or solution, we define another function of the form another non-linear. Let me define that function also. Another non-linear partial differential equation of first order, right? Okay, so it is expressed as f of x comma y comma z comma p comma is equal to 0. So it should be non-linear partial differential equation, right? Okay, so if I did not define f over here, yeah, I should define over here. F of x comma y comma z p comma q is equal to 0. This is the general expression. This general method solve non-linear partial differential equation of first order of this form, and this is another another equation. Now you have to solve f and capital F, right? And from this you will get some p is equal to p of x comma y comma z comma a, and q is equal to q of x comma y comma z comma a, right? Don't worry, it's just theory which I am telling. You can just note it for now, and we will see it using some problems. It is just some theory part which you can remember or you can note for your reference purpose, because of course theory is important to solve any question or to understand any concept, right? That is why. Let me write it, then I will tell everything. So when we substitute P and Q, we get some phi of x comma y comma z comma a comma b is equal to 0, right? Okay. Now let me tell what it all means. So basically, Charpit's method is a generalized method, or is a general method to solve a non-linear partial differential equation of first order of the form f of x comma y comma z comma p comma q, where p is equal to del z by del x and q is equal to del z by del y. Correct? Okay. So basically, in this we are going to apply this rule that dz is equal to del z by del x dx plus del z by del y dy. We can write as p dx sorry, plus q dy, correct? Okay, you can just solve this expression, and then you will get some relation which we will see using questions. And to get this desired result, what we are going to do is we will define another nonlinear partial differential equation of first order capital F of x comma y comma z comma p comma q, right? And then we are going to solve p and q, and from that we will get some result that p is equal to this expression, q is equal to this expression. And when we will substitute back in this equation the values of p and q, we will get some phi of x comma y comma z, this is z comma a comma b, right, is equal to 0. So this is the whole procedure of Charpit's equation, Charpit's method. So it is like straightforward, but the biggest question is that how we will define this another function f of where is it, yeah, f of capital F of x comma y comma z comma p comma q is equal to 0. How we will define this function, because we will be given this function, so how we will go from that to that? to this. I mean, well, let me explain it now. Let's see that. Let me raise this. To determine f. How will it determine f, right? So let's see it. So we will differentiate f and capital F with respect to x and y. Of course, we have to differentiate. This partial differential equals we have to differentiate, right? So we will have if we differentiate del f by del x plus del f by del z dot del z by del x, del z by del x. So del z by del x I can directly write p because it's like we are dealing with del z by del x again and again. So by now you must have practiced, you must have practiced that we can write p directly over here, plus del f by del p dot del p by del x plus del f by del q dot del q by del x is equal to 0, right? And second one, it is del capital F by x plus del capital F by del z dot p plus del capital F by del p dot del p by del x plus del capital P by del q dot del q by del x is equal to 0. Okay, yeah, I know it's like too much complex. Well, I made a video recently of 10 minutes. In that I have explained that if a function is u of x comma y comma z, which I have already shown in the previous part only, that I had made that like that video, you can refer to that so that you can easily understand this expression if you are not able to understand. But it is basically a chain rule which I am applying, nothing else. Chain rule and product rule, that is it. So in this, we have differentiated it with respect to p, with respect to x, and in this we will eliminate del p by del x. We have to eliminate, right? We have to eliminate, okay? And this is the expression. Now, if we will differentiate it with respect to y, what we'll get? We'll get del f by del y plus del f by del z dot q, correct, plus del f by del p dot del p by del y plus the expression del f by del q dot del q by del y is equal to 0, correct? Yeah. And second expression del capital F by del y dot del plus sorry del capital F by del z into q plus del capital F by del p dot del p by y, sorry, del y plus del capital F by del q dot del q by del y is equal to 0, right? So in this, eliminate del q by del y, right? Okay, so let me just see all these expressions are correct or I made any mistake. I have to just check it once. Yeah, it's this one is correct. Yeah, it is absolutely correct. And this expression is absolutely correct. This one, yeah, it is also correct. And del phi, yeah, it's also fine. Yeah. And now let's see this one. It is yeah, this expression is correct. This expression, yeah, okay, yeah, correct. And this one is also correct. Yeah. So in this we will eliminate del phi, I mean del q by del y and del p by del x, and then we will do some other mathematics which we will see in just few minutes. Let me erase this. So on eliminating del p by del x, what you will get is that the first expression as del, it's a big expression, so I should write it from here. So it is del f by del x dot del capital F by del x, I mean del p, minus del f by del x dot del small f by del p, this plus del f by del z dot del f by del p minus del f by del z dot del f by del p into p plus del f by del q dot del capital F by del p minus del f by del q minus del q dot del f by del p into d into del phi del q, sorry, del q by del x is equal to 0. Okay, this is from the elimination of del p by del x, right? Okay, let me see this if is it correct. Yeah, del phi this and then this expression. This is capital F and this expression, this is again capital F only. Yeah, it's correct. Yeah. Now the second expression del F by del u, sorry, del y dot del capital F by del p minus del F by del x dot del F, sorry, what is it? Yeah, del F by del q. Yeah. Okay, del F by del y into the quantity del F by del q minus del F by del y. Sorry, yeah, del y, and then del F. Yeah, correct. Plus the expression del F by del z dot del F by del q minus the quantity del F del capital F by del z dot del F by del q plus the expression over here. It must be there must have been a q over here. Let me see it. I think there is some problem in this expression. This del f, and when we will eliminate this, yeah, there will be a q in this expression, because of course if it won't be a q, then there will be a problem. Yeah, so okay, let me see it. Plus del f by del q, del f by del q dot del f del capital F by del q minus del capital F by del p dot del f by del q into the quantity del p by del y del p is equal to 0, and this is from the elimination of del q by del y, correct? So let me see this expression. I have to confirm that whether it is a q or not. So let me think once that if we are going to add this expression, then what we'll get. So yeah, here it must be a q, right? Because of course you can see the pattern also, and when you eliminate, you will see that there's a q, of course, right? Of course, without q, how can you form a expression y, right? So yeah, this is the expression, and now you have to add them. You have to add them now. So when you will add them, what we will get is that it is a very big expression now. So it is del, I have to write bit small, let me use another chalk, this one. So it is equal to del f by del x. Of course, I'm not showing the calculation because calculation you can do on your own. I've already written the results which we will get, because of course calculation is like elimination. It's like you studied in 11th, 12th and maybe lower class also. That is why I'm not showing that. I'm directly writing the result of elimination, right? It is just elimination, which you know, of course, right? That is it. So del f by del x plus p del f by del z into the quantity del capital F by del p plus the quantity del f by del y. Don't worry, these are just very big expressions, but when you will solve the problems, you will see that it is very easy thing which I am telling you all. It is just a generalized expression. That is why it is like felt that it is a very like very difficult topic. No, it is very simple. Once you will see the question, you will see that it was so simple, right? So just wait for a minute. Plus the quantity q times del f by del z times the quantity del f by the quantity del q plus the expression minus p del f by del q, I mean del p minus the quantity q del f by the expression del q, right? Okay, this is del f by del z, okay, plus minus del f by del p del f by del x plus minus del f by del q df by d, sorry, del y by del, sorry, del f by del y is equal to 0. So this is the expression, right? Okay, so what we are going to do this, what we are going to do with this expression? Well, it is a very simple thing now. Let me show you how. Now, just see this expression. You can easily say from this that this expression is a linear partial differential equation. It is a Lagrange's linear partial differential equation in which x, y, z, p, q are independent variable, and f is a dependent variable, right? Dependent variable, right? Of course, it is del f by del p, del f by del q, del f by del z, del f by del x, del f by del y, right? So x, y, z, p and q, these are the dependent variables. I mean, these are the independent variables, and f is the dependent variable on x, y, z, p and q. Right? Of course, we had that f of x, y, z, p, q is dependent on these quantities, right? So we can apply that rule that we had previously proved it for like x, y and z only. Now we can extend that idea to x, y, z, p, q and f, right? So we will have dx by dy by dz by dp by dq by f df by 0. Why 0? Because of course over here it is 0, right? So what is this expression? Negative del f by del p, negative del f by del p, right? Yeah, and that negative del f by del q, correct? And this expression negative p del f by del p minus q del f by del q. Just watch the Lagrange's auxiliary equation part, so that you will understand. So from that you will understand that why am I writing it like this, right? Okay. So this expression, and then for p it was, yeah, it is del f by del x plus p del f by del z, correct? And for this, it is this expression del f by del y, del f by del y plus the quantity q del f by del z, q del f by del z, correct? Understood? Let me verify. Is it correct? Yeah, this is correct. This is equal to 0. With respect to z, it is equal to negative. And correct. And with respect to dp is equal to del f by this. Yeah, correct. So from this, you will get the values, the required values, whichever you want. And from that, you will get the value, basically you will get the value of p and q. So from that, you will integrate dz is equal to del is equal to p dx plus q dy. Just integrate that expression, you will get the value of z. This is how we will work. So let's see a problem to understand this expression, right? Let me raise this. So let's see the question. Solve 2zx minus px square minus 2qxy plus pq is equal to 0. Correct? Okay. So basically it is of the form that f is equal to 0, right? Basically f of x, y, z, pq is equal to 0, right? Equal to 0, right? Okay. So let's solve this. So you have to find del f by del x first of all. It will be equal to 2z minus 2p 2xp minus 2qy, right? Correct? Yeah. Del f by del y, it will be equal to what? It will be equal to negative 2qx, right? Okay. And del f by del p you need to find now. So del f by del p, it will be equal to what? It will be equal to negative x square plus q. Negative x square plus q, and del f by del q, it will be equal to this expression that it will be equal to q minus 2xy, correct? Right? Yeah, correct. Okay. So from this, you know the expression that dp by the expression del f by del x plus p del z by del f by del z is equal to the quantity del q del q sorry dq by del f by del y plus q del f by del z is equal to the expression that it is equal to dz by the quantity negative p del f by the quantity del p minus q del f by del q, right, is equal to dx by the quantity negative del f by del p is equal to dy negative del f by del q, right? Okay. Now let's solve this expression. So it is equal to 2z minus 2xp minus 2qp, right? We have this expression, and when you find del f by del z, it will be equal to 2x. It will just equal to 2x, right? Okay. So let's write this expression. So we will get dp by what is del f by del x? Del f by del x is 2z minus 2xp minus 2qy, and what is del z by del f by del z? It is equal to 2x multiplied by p. So this expression and that expression will get cancelled. So we'll get 2z minus 2qy is equal to dq. What is dq? dq is negative 2qxy, negative 2qx, and what's del f by del z? It is equal to 2x. When you multiply by q, it will become plus 2qx, so it will be equal to 0. Correct? Okay. So dz by, similarly you will solve over here also, you will get px square minus 2qx plus 2pxy, right? dz by px square minus 2pq, sorry, right? Okay. Of course, these are just you are substituting these values, nothing else. Okay. That is why I am just writing it like that. Okay. It is dx by inverse negative del f by del p. It is equal to x square plus x square minus q, and it is equal to dy by this expression. You will get 2xy minus q. 2xy 2xy. Wait, why I have written q over here? Sorry. It will be p. Sorry. It will be p over here, right? Minus p, right? Now you can take this expression as it is. So you will get that dq by 0, right? It means that dq must be equal to 0 to make it defined. So we can say that q is equal to some c1, some constant c1. Okay. Now when you have got the value of q as c1, you can substitute it over here to get the value of p. So when you substitute there, you will get 2zx minus px square minus 2c1 xy plus cp is equal to 0, and when you will solve, you get p is equal to what? P is equal to 2x times c1 z minus c1y by the quantity x square minus c1 square, right? Correct? This c1 is squared, right? So basically we solve for Q, then we substitute over here. From that we solve for P, right? So we have the value of P, we have the value of Q. So we can now just solve it like that. So uh, I should write, where I should write. Okay, let me erase this, just a minute. Let me erase this so that I can write it. So yeah, so I have this expression that dz is equal to p dx plus q dy. So we are just going to solve this now. So it is simple. Dz is equal to the expression 2x 2 minus, sorry, it is z z minus c1 pi divided by the expression x square minus c1 square dx plus c1 dy, correct? C1 dy, okay. Now you can solve this expression, right? So now you can easily solve this expression because now it is just ordinary differential equation which you know how to solve it, right? So basically what you can do is you can divide by both sides by z minus c1 y, and consequently you can solve it. Let me show you how. You can say from that dz minus c1 dy is equal to 2x by x square minus c1 square times the quantity z minus c1y dx. So from this you can say that d of z minus c1y by z minus c1y is equal to 2x by x square minus c1 square dx. You can integrate this. Now it is of the exact form. You can just integrate this, right? So this is how we solve the problems using Charpit's method. And of course, the method which we used in its derivation, it is a very lengthy method, but when you solve questions, then it is like very simple, right? Understood? So let me raise this, and then we move to the next topic, that is the homogeneous equations. Let's see that. Now let's start with homogeneous linear equation with constant coefficients. Let's start with this. Okay, so let's start. So what is meant by homogeneous linear equation? Well, let's consider a partial differential equation of the form a naught. Let me write it. A naught del n del z by del x n plus a1 del n z del n minus 1 x del y a2 del nz by del n minus 2 x del y square, and so on till the expression an del n z by del y n plus, yeah, plus b0 del n minus 1 z del x n minus 1 plus b1 del n minus 1 z del n minus 2 x del y. This is where, wait, sorry, it should be del x n minus 1. This is 1, this is the other is correct. Where it should be at del x n minus 2, yeah. So this expression, then this over here, del x n minus 2 del y, and so on like this. And you have to go till like till all the expressions till suppose k naught del z by del x plus k1 del z by del y plus some l naught times z is equal to 0. So you can write it as phi d dot d dash of the quantity z is equal to 0, right? Where d is equal to del by del x and is equivalent, and d dash is the operator, del by del y, right? Okay, so this is called a linear partial differential equation of nth order with constant coefficients. We haven't discussed till now homogeneous linear equation. We have to discuss that now. So this is a linear partial differential equation of nth order with constant coefficients, right? So a linear homogeneous partial differential equation. Now let's discuss that. So it is a linear homogeneous partial differential equation is of the form where all the derivatives are of same order. So if we remove all this expression, if we just see this expression a naught, if I write in summation form, is it okay? Right. So it is as I goes from 0 to n, ai del n z by del x n minus I times del y I is equal to 0. This expression is called homogeneous linear partial differential equation, right? So the condition is that where all derivatives are of same order. So in this it is of same order, right? Correct? Okay, so nth order basically, if I say, right? This is called a homogeneous partial differential equation, right? Okay, so yeah, and if you want you can write it like this also. A naught d n plus a1 d n minus 1 d dash and so on into z is equal to 0. Applied on z is equal to 0. This is an operator basically. Remember from ODE we had certain operators similar as the case over here. Just in this we have two operators. There we had only d by dx. Here we have del by del x and del by del y. We have two operators over here, right? Simple. So let's see how we find its solution. So let's see that. So in this also we apply the same method as we did in ODE. We will find the complementary function and the particular integral, and then we will add them to get the general solution, right? So complementary function and pi we need to find, right? So complementary function, so suppose it was like phi of d dot d dash z is equal to some function f of xy, suppose it was this expression. Then what we do is that in this case, to find CF, what we do, we set phi of d dot d dash z as 0. We don't consider this. And then we find the solution according to this. And then we solve for pi d dot d dash z is equal to the function x comma y. And then we solve for the pi in this case, and then we club these two results together, cf plus pi, to get the general solution, right? So this is how we do it. Okay, so yeah, this is just the theory part, and of course it is free from any arbitrary constant. Okay, and over here you will get arbitrary constants, right? Okay, so let's see a problem, or before that let me discuss how we'll find uh, the CF. Let's discuss that also, and then we will be seeing a problem to understand it better, right? Okay. Okay, so let's consider a function, a differential equation, del 2z by del x square plus a1 del 2z by del x, del x del y plus a2 del 2z by del y square is equal to 0. Correct? This is the expression. So if you have studied ordinary differential equation, you must be knowing something called an auxiliary equation, right? So how we define auxiliary equation in this case? Well, I can write it as d square z plus d dash z plus, a1 times plus a2 times d dash whole square is equal to 0, right? Okay. Now I will write it as an auxiliary equation m square plus a1m plus a2 is equal to 0, where m is equal to d by d dash. Correct? D is equal m is equal to d by d dash. So here m is a numeric value basically, right? So from this you will solve for the values of m, and then you can factorize this as suppose you get the result as m1 and m2, you get this result. So you can factorize it like minus m1 z into this quantity into the quantity d dash minus m2 z is equal to 0, right? Like this you can do. Okay? So this is how you will solve. Okay, so let's see how you solve it. Let's take some cases to understand this. Okay, let me raise this. So let's take the case 1 in which m1 is not equal to m2. Means m1 is not equal to m2, right? So in that case what we will get is that we'll be having this expression d minus m1 d dash times sorry, over there did I wrote this expression d minus m1 times d dash minus m2. Sorry, if I wrote this then please change it. It is not this, it is this expression d1 times d minus m2 d dash z is equal to 0, right? It is wrong, it is wrong, it is wrong, it is absolutely wrong. Sorry. So this is the expression. Okay, so what you can do is that you can set each of them as equal to 0, then you will apply the linear combination of the solutions. Okay, so d minus m1 d dash is equal to 0, of course applied on z. This is applied on z is equal to 0. So from this what you can do is that it is very simple. So dz minus m1 dz d dash z is equal to 0. So basically it is del z by del x minus m1 del z by del y is equal to 0. So it is basically equal to p minus m1 q is equal to 0. So we will apply it as a Lagrange linear partial differential equation. So you will get dx by 1 is equal to dy by negative m1 is equal to dz by 0. Correct? Correct? So from this you will get that z is equal to some constant, and from this when you solve it, it is like very simple, is y plus m2 because we have taken m1, so it will be equal to x, right? Okay, so from this we can say that z is a function of this, what I am writing is equal to y plus m1x is equal to some constant a. So from all this we can say that because from the arbitrary functions which we know how we defined them, we can say it like it is equal to function of y plus m1x, right? And we can also say that z from this one, from 2 1, we can say f is equal to y plus m2x, right? Correct? So this is the solution, right? So we can say that z is equal to f, this f1 f1 times y plus m1x plus f2 times y plus m2x, right? Okay, and of course there is no need to do linear combination because of course if you multiply by c1 or c2, then also it will be just the same function. I mean it will be also included in that function, because of course c1 times x can be written as x only, capital X only, right? You can write it like this because of course c1 is just a constant. So even if you multiply it, it will be absorbed in that expression only, in that function only. So it's not required actually. Okay. So okay. So let's see a problem to understand this all concept. So let's see it. Okay. Let me raise this. So let's see the question. It is 2 del 2z by del x square plus 5 del 2z by del x del y plus 2 del 2z by del y square is equal to 0, right? Okay, so let's solve this. So again it can be written as 2d square plus 5d d dash plus 2 d dash square z is equal to 0, applied on z is equal to 0. Correct? Okay, so we can rearrange it as 2m square plus 5m plus 2 is equal to 0, right? The auxiliary equation. This is the auxiliary equation. Auxiliary equation. Correct. Now you can solve this easily. You will get what? You will get 2m plus 4 into m plus let's solve it only. So you will get 2m square plus 4m plus m plus 2 is equal to 0. So you will get 2m m plus 2 plus m plus 2 is equal to 0. So you get m is equal to negative 2 and negative 1 by 2, right? So you will get clearly that z is equal to some f1 of y minus 2x plus f2 of y minus x by 2. This is it. Simple. Okay. Yeah. So basically, of course, you have to apply the complete rule that over here it will be d minus d dash 2d dash into d minus d dash by 2 into z applied on z, sorry, and then you will just write d minus 2d dash applied on z is equal to 0. Then you will say that dx by 1 is equal to dy by the quantity negative 2 is equal to the expression what? It is equal to dz by 0, and then you will solve this again to get the result. Okay, so it is like a linear method which you will apply. So basically this is how you will solve, right? Let me see if it is correct. Yeah, sorry, it will be plus, right? It will plus over here, and then you will solve. You will get this expression, right? And when you will solve, you will get this expression, right? Okay, this is how you will be solving. Okay, and now let's see to the next. Let's move to the next case in which this is simply ordinary differential equation. If you remember what I am doing over here, it is all that. It is just over here. There's an extra step of applying Lagrange's linear partial differential equation, but this auxiliary equation, Lagrange's auxiliary equation, which we are applying, right? Just everything is same as we did in ordinary differential equation. Understood? Okay. So now let's move to the next case. Basically, let's see. So let's see the case 2 when m1 is equal to m2. So in that case, what you will get? So in that case, we will assume d minus. Basically, it will become like d minus md dash, applied on z is equal to 0. Of course, this will be the expression, right? Okay. So in this case, when we will apply it, we will say d minus md dash applied on z as equal to u. We will set it equal to u, okay, and then we'll apply d minus md dash applied on u, and then set it equal to 0, right? Okay. So let's start with this expression, okay. So from this, when you will solve, you will get this is that only partial differential equation. Sorry, when m1 is not equal to m2, that case only. When we will solve it, you will get u is equal to some function of y plus mx. Correct? That is only, if you remember, right? Okay. And just when you will move to this expression, you will get del z, basically dz minus d dash m d dash z is equal to u is equal to f of y plus mx. Correct? Okay. Basically, here also you will apply Lagrange's partial differential equation, linear partial differential equation, the auxiliary equations you will form, and then you will get this result only. Basically, in that case also, when we were getting m1 and m2, and then we were saying that d minus m1 d dash is equal to 0, applied on z is equal to 0. So from that we were solving z is equal to f of y plus m1x. So similarly over here we get u is equal to f of y plus mx. Simple, right? Okay. So this expression, and we will get p minus m q is equal to f of y plus mx. Correct? So we have dx by 1 is equal to dq by negative m is equal to dz by f of y plus mx. Correct? We have this expression, right? Sorry, this is dy. I am writing this. Okay. Now we have to solve this expression. So how will we solve it? Well, dx is equal to this expression, we can say. So dx is equal to dz by f of y plus mx. Simply we can solve this expression. So what we can do is that we have to do something over here. So let's keep it aside for now. And when you solve these two expressions, you will get y plus mx is equal to some constant a is equal to some constant a. So y plus mx is basically over here a f of a, which is a constant. So you get that x is equal to z by f of a plus some b. So you get b is equal to x minus z by function of y plus mx, right? I got two constants from this, okay? So you get these two, so you get the expression as z is equal to what? Z is equal to, we can say from here that, or we can clearly say from here that instead of doing this, we can say it like this also, that let me show you. We can say it like z is equal to f of a times x plus b f of a. Now b f of a is again a constant. Let's name it b only itself. So we get z is equal to f of y plus mx into x plus b. So it is minus and it is equal to this, right? So from this, where I can write z is equal to, so we can say z minus f of y plus mx into x is equal to this expression f of, this is f1, this is f2, y plus mx, right? So we get z is equal to f1 y plus mx x plus f2 plus f2, this is y plus mx again, right? This is the expression, okay, correct? So it is equal to this, yeah, correct. So now suppose if you have n powers included, suppose it was like instead of 2 here, it would have been, if there would have been 3 expressions, then you would have get z is equal to phi 1 y plus mx plus phi 2 y plus mx x plus phi 2 y plus mx x square, right? Correct? Okay, this is how you write. So phi 3, correct. So let's see a question to understand this. Let's see. So let's see a question. 4r minus 12s plus 9t is equal to 0. What is rs and t? If you remember, I told what is r, what is s, what is t. So let me write it. It is 4 del 2 z by del x square minus 12 del 2 z by del x del y plus 9 times del 2 z by del y square is equal to 0. It is similar to saying this. That is, I am trying to show the problems in such way that even if notations come, then also you can easily do it. Okay, so that is how you express it. So now let's write its auxiliary equation. It is 4m square minus 12m plus 9 is equal to 0. So when you will break it, you will get 4m square minus 6m, yeah, plus minus 6m plus 9 is equal to 0. So you can take 4m as common, sorry, 2m as common, so you get 2m minus 3 plus, you can take negative 2m 2 as common over here. 2m minus 3 is equal to 0, sorry, 3, right? So from this you can get, we will get 2m minus 3 times 2m minus 3 is equal to 0, right? So we get m is equal to 3 by 2 and 3 by 2. So m is equal to 3 by 2, right? So again you have to apply that whole procedure, but I will directly write the answer over here that z is equal to phi 1 instead of f1 I am using, phi1 you can use whatever you want. Y plus 3 by 2 x plus x times phi2 y plus 3 by 2 x. This is the complementary function. This is the complementary functions which we are calculating right now. Okay, is it correct? Yeah. So let's move to the next topic, rules for finding pi. Let's see how we find the particular integral, and then we will be well acquainted to learn that how we find the general solution. So let's see that. So let's see the rules for finding pi, that is particular integral. So let's see it. Rules to find pi. So before seeing the general method, let's see some of the standard methods or the formula to calculate the particular integral. So let's see that first of all. So let's see that. Okay, they are called the short methods. Let's first of all study short methods to find pi, right? Okay, so first one, when f of x comma y, that is the given function, is of the form e to the power ax plus by, then in that case particular integral is equal to 1 upon phi of d dot d by d dash, I mean d comma d dash, d d d dash e to the power ax plus by d comma d dash, sorry, is equal to 1 upon phi of a comma b e to the power ax plus by, provided that phi a comma b is not equal to 0. Listen one thing, if I wrote there phi of d dot d dash of z is equal to 0, then change this and write this is wrong, d comma d dash is equal to 0, right? Okay. So you should write this expression instead of that. Okay, so pi is equal to this expression for this case. Okay, because of course we are expressing it in terms of parts. Okay, so that is why. Okay, so this is the first one. Then see the second one. Second one, it states that function of x comma y, function of x comma y, if it is equal to sine of ax plus by or cos of ax plus by, correct? If that is the case, then in that case particular integral is equal to phi of 1 upon negative a square negative ab negative b square into the quantity sine of ax plus by is, that is it. Okay, and this expression must not be equal to what? Must not be equal to 0, right? So let's see the third case. Let's see that also. So, and then we'll see the general case. That is better to discuss the general case, because this already can find for any value, any function. This is just some standards, that is the end discussion. Okay. So I'm not discussing the third one because it is like a bit complex, and instead of applying that method, you can easily do it using generalized method. That is why I'm not discussing that. Okay. If it will be required, I will make a video on it. Like 5 to 10 minutes, you can watch that, but for now let's discuss something which will help you to understand concepts better instead of like learning those things. Okay, so let's see the general method. So pi is equal to, similarly as you did in ODE, you have to apply the same rule in case of pi also. It will be the inverse basically, d comma d dash of the quantity x comma y, which is equal to 1 upon, now as you just did before, d minus m1 d dash, d minus m2 d dash, and so on till d minus mn d dash, correct, of the expression f of x comma y, this expression. Okay, so what we are going to do, suppose we are evaluating 1 upon d minus m d dash, a general one, f of x comma y. So we will set it equal to some variable, suppose z. So you will get, of course, when you bring it over here, you will get f of x comma y is equal to d minus m d dash applied on z And now it is that expression only in which m1 was equal to m2. It is similar to that. It is exactly same like that. So we will apply the Lagrange auxiliary function in this case, and you will again get the answer, right? So let's discuss it with respect to a question. So with reference to a question, so you can easily understand this. Okay. So let's discuss it. Okay. Let me raise this stuff. Del 3z by del x cube minus 2 del 3z by del x square del y is equal to 2 e to the power 2x plus 3x square y, correct? This is square, okay? So let's evaluate this expression, and as an homework you can do this question also. You can do this as practice. Del 2z by del x square minus del 2z by del x del y is equal to cos x cos 2y, correct? You can do this from your part. I will discuss in this one, okay? So let's discuss this. Let me stop here. So let's see solution. So again we will find the auxiliary equation. First of all we will find the CF. So first of all let's find the CF. What we will get, let's see it. So when we find the CF, we can say it as m cube minus 2m square. I'm not writing the statements that you can do on your own, right? I'm writing the concept which you need to follow in this. From this, you will get m is equal to 0, 0, and 2. Of course, not 0 and 2, 0, 0, and 2, because over here it is m square, it is a degree of 3. So, of course, you will get 3 results in this, 3 solutions. So, that is why you will get 0, 0, and 2. So, there are 2 equal solutions in this case, right? Okay. Basically, m square is equal to 0 implies m times m is equal to 0, which implies m is equal to 0 or m is equal to 0. So, basically, 2 solutions. Okay. Yeah. So you can say that CF is what is equal to CF is equal to phi 1 of y plus 0x plus x times phi 1 of y plus 0x plus phi 3 of y plus 2x, correct? So you get phi 1, this phi 2, sorry. So you get phi 1 of y plus x phi 2 of y plus phi 3 of y plus 2x, correct? This is the expression, yeah. So from this you will get your CF value, right? Okay, this is how you will get, yeah. And now you will find the PI, right? So let me write the CF over here. This is your homework. You will do it. So CF is basically phi 1 of y plus x phi 2 of y plus phi 3 of y plus 2x, correct? Okay, let me erase this stuff. So now we are going to find Pi. Pi will be equal to 1 upon phi of d comma d dash of the quantity f of x comma y. So it is equal to 1 upon d dot d into d minus 2 d dash of the quantity e to the power 2 times e to the power 2x plus 3x square y, right? This expression. So what we are going to do is that we will assume 1 upon d minus 2d dash as into 2 e to the power 2x plus 3x square y as some t. We'll assume it as t, and then what we are going to do is that we will solve for this expression. So I'm writing directly, it will be equal to p minus 2q is equal to 2 e to the power 2x plus 3x square y, right? We will get this expression. So we have dx by 1 is equal to dy by negative 2 is equal to dz by we will have dz by this expression, right? We will have dz by this expression. Sorry, dz, not dt, not dz, because we assumed over here dt as means this as dt as t. Sorry, 2 e to the power 2x plus 3x square y. Now we have to solve this. So first we will get that y plus 2x is equal to a, some constant, right? And the second expression which we are going to get is that we will
set this expression equal to this expression, and then we are going to solve this expression. So let's see how we will solve it. Let me raise this. So from this we will get that dt is equal to 2 into e to the power 2x plus 3x square into what is the value of y? Y is equal to a minus 2x. From this we can say a is equal to, y is equal to a minus 2x. So a minus 2x dx, right? Just integrate this, you will get the value of t. And of course, here there will be no arbitrary constant because it is particular integral, right? So from this, when you will solve it, you will get some expression which I think I should write. Okay, so when you will solve it, you will get some expression. Suppose your t is equal to some z, suppose some alpha, you get some function alpha, right? Alpha of x comma y. Okay, suppose you get, or you can just integrate it simply. Let me integrate it. It is this is e to the power 2x plus ax cube minus 6x cube minus 6x cube minus 6x to the power 4. So it will be 3 by 2, right? This t. Okay, this, let me check, is it fine? Yeah, 3 by 2, yeah, correct. And then you can substitute it as 2x plus y, and now you have 1 by d dot d dash into uh, this expression t, right? And set it equal to u. So you will get 1 by d t is equal to u. So you will get du is equal to t. So you will get over here del u by del x is equal to t, right? So from this you can say that t is equal to t, hence you will have dx by 1 is equal to dq by 0 is equal to d u by t. And what is t? We know the value of t is this. From this you will solve for z, you will solve for, sorry, you will solve for u, right? You will get some value of u, and then you will have 1 upon d into u is equal to z, you will do, and then you will solve for z, and that will be equal to your pi, right? And then you will do cf plus pi, right? Simple. So I showed you for one expression 1 upon d minus 2, and then you will solve for this because it is very simple, because it is not involving a 2 in this case, right? So this is how you solve for pi basically, right? And if I have to write the final answer, pi will come out to be, pi will come when you will solve e to the power 2x by 2 plus x to the power 6 by 60 plus y x to the power 5 by 20, right? So you know CF, you know PI, so you can clearly find the general solution as CF plus PI, right? Where I have written CF plus PI is equal to the general solution. Okay, simple, understood? Okay, so let's see what we can do next. Yeah, let's just start with another topic now. Okay, so do this problem on your own and complete this also. I've told one method, and then I've told for one means 1 upon d minus 2, you can solve for 1 upon d and then again solve for 1 upon d, right? Understood? So now let's start with non-homogeneous linear partial differential equation, right? So how we will solve for this? Then for example, a linear partial differential equation which is not homogeneous is called a non-homogeneous partial differential equation. Okay, so basically suppose if I have phi of d comma d dash of z is equal to some function of x comma y. So it is not homogeneous if it is if all its derivative don't have same order. For example, if I say d square plus 2d dash plus d dash square minus 2d dash uh, applied on z is equal to some function of x comma y. So in this case, we can say that we can see that this expression is of order 2 and it's of order 1, right? So of course, it is not of same order, so that is it is a non-homogeneous linear partial differential equation, right? So what's next we can do? How do we solve such kind of expressions? Well, In this also we will use CF and PI method. So we won't discuss for PI because in this case also PI is solved using that same method only which we are doing, right? That factorization and then setting it equal to some other variable, then using Lagrange equations to solve that, okay? Lagrange auxiliary equations. So in that case, we will be applying, so for PI, we will be applying the same method. So we won't discuss that. For CF, there's some manipulations which are required. Let me discuss that so that it becomes easier for you. Let me discuss that. So in such cases, we can factorize the expression as instead of d minus md dash, there comes another constant as a. Just that's the difference in calculation of CF, right? When you factorize, you will get such expression, right? And applied on Z is equal to 0 because we find the CF, right? So now what we will do is that we will open it. We will get P minus MQ minus AZ is equal to 0. So we get one, so we can say P minus MQ is equal to AZ. Now again, it's Lagrange's auxiliary equation. That's all it is, right? So we get, yeah, divided dz by az, right? Y plus mx a, not a because we have already used it. Let's name it as c1, and then dx is equal to dz by this expression. So we get dx is equal to dz by z and a. So we have ax is equal to natural log of z plus some constant. So we can say, or uh, some constant we can say c2, okay? So from this we will get z is equal to e to the power ax, and you can say plus some c2 again, right? There's no issue in that. So this is how you will solve for this, or you can say it as c2 times e to the power ax. Let's name it as k for now, and then we will rearrange it like this. Okay. So we get this. So in this case, CF is equal to, well, z is equal to e to the power ax times the function of y plus mx. This is how you find the CF in this case, right? Okay. No need of F1 because we were just dealing with one expression, okay? So if we have multiple such expressions, suppose the product from d square minus mi d dash minus ai applied on z is equal to 0, I goes from 1 to n. So of course when you will open it, it will become d square minus m1 d dash minus a1. Wait, it will be, there will no d, sorry, there will no d square there. Yeah, when you open it 1, you will get d minus m1 d dash minus a1 multiplied by d minus m2 d dash minus a2, and so on and so forth till d minus mn d dash minus an whole applied on z is equal to 0, right? That is the expression which we are going to get, okay? So this is the expression, and when you will solve it, you will get the answer as z is equal to e to the power a1x f1 y plus m1x plus so on till e to the power a n x fn of y plus mn x, right? This is the expression, okay? A1 is it, yeah, this expression, yeah, this is okay. And you can express it in form of summation also, that z is equal to like sum of all those expressions, okay? That's okay. So this is how you solve for z and all. And yeah, suppose if uh, repeated this, suppose if this expression is repeated, for example, d minus m d dash minus a times d minus m d dash minus a, and so on, means the m and a are equal, then in that case z is equal to e to the power ax f1y plus mx plus x times e to the power ax f times y plus f2 times plus mx, and so on till, if it is repeated n times, then you will have plus e to the power uh, plus x to the power n minus 1 e to the power ax fn of y plus mx, correct? Just like in that expression, but over here we have an extra expression of e to the power ax. That's it. Okay. So yeah, that's it. Is it fine? Yeah. Okay. So now let's discuss it with reference to a question, so it becomes easier for you all to understand. Let's discuss it with reference to a question. So let's see the question. It states d square minus plus 2d dash minus 2d, sorry, plus d square d dash square minus 2d minus 2d dash applied on z is equal to sine of x plus 2y. So let's calculate first of all CF. What you will get is that CF, when you will factorize it, you will get d minus d, and then you will get a plus 2, here plus, and this over here minus. You will get this expression, and then you will have d plus d dash is applied on z is equal to 0. Correct? Is it correct? Yeah. So of course, now it is very simple. You can easily solve it. You will get z is equal to e to the power ax 2x f1 of the quantity y minus x plus f2 of the quantity y minus x. Correct? Yeah. Of course, this is a homogeneous. This is a non-homogeneous, right? Expression. This is a homogeneous expression. This is not homogeneous expression, right? So we got CF. This CF. Y minus x plus f2 times y minus x, right? So let's see how we'll find the pi now. So let's calculate pi. Okay, so let me erase this. Yeah, so let's see pi. So how we'll find pi? Well, we are just now factorizing this expression, so now let's evaluate this. So pi will be basically equal to 1 upon d plus d dash multiplied by d plus d dash minus 2 applied on sine of x plus 2y. So let's set it equal to t for now. Okay. So from this, when we are going to evaluate this expression, so what we are going to get is that d dash d plus d dash minus 2 applied on t, applied on t, it must be equal to what? It must be equal to this expression, sine of x plus 2y. Or let's first of all do it with reference to this, because you already know how to solve such kind of expressions, right? That is why. Okay, so when you will open it, you will get p plus q is equal to sine of x plus 2y. So apply Lagrange's auxiliary equation, so you will get dx by 1 is equal to dy by 1 is equal to dt by sine of x plus y, right? You will get x plus 2y, sorry, x plus 2y. So from this you will get y is equal to y minus x is equal to some constant c1, and then you will just substitute that dt is equal to sine of x plus y dt. So you can say it like x plus y can be as 2x plus y minus x, and what is y minus x? It is equal to c1, right? From this expression y dx is equal to dy, you will get y minus x is equal to c1, right? So this, now you can easily evaluate this expression, whatever, sorry, dx over here, you will get some value, some expression of t. Then you will again put it over here, and when you will put it, from this what we will get? We will get the expression as it will be equal to sorry, negative cos x plus 2y by 3. We will get this expression. Now we will substitute it over here. So let's see what we are going to get when we substitute over here. So we will get 1 upon d plus d dash minus 2 applied on this expression, that is negative of the quantity cos of x plus 2y by 3 right? So let's assume it as z. Let's assume it as z. So from this we will get, let me write it directly now. P plus Q minus 2z is equal to negative cos of x plus 2y by 3. Is it okay? Dz is equal to P, d dash z is equal to Q, and it is equal to negative 2z. Okay, fine. Okay, so from this it is equal to plus 2z. We can say, so dx by 1 is equal to dy by 1 is equal to dz by 2z minus cos of x plus 2y by 3. This is the expression. So from this you will get y minus x is equal to again a constant, suppose c1, and then when you will solve this expression, what you will get is that, so we can say x minus y or y minus x, whatever you want to say, you can say it like that. Okay, so from this, how we'll solve it? Well, now it's a tricky part, so let me erase this and then we'll discuss. Now we can say dz by dx is equal to 2z minus cos of, well, we had the expression y minus x is equal to constant, right? Or you can say x minus y is equal to constant. Both are equal, both are same, right? So when you will say this, you will get the expression as 3x minus 2c1, right? Now it is a linear differential equation, an ordinary linear differential equation. How? Because it is dz by dx and it is z and it is a function of x. It is a linear differential equation which you can easily solve it by finding the integrating factor e to the power e to the pdx, and then you can solve it, right? So I leave this to you. You can easily solve this expression, right? Understood? And of course, you have to remember that in particular integral, there will be no arbitrary constant after you evaluate everything, right? And in fact, whenever you integrate also, there won't be any arbitrary constant, right? Okay. Yeah, it was auxiliary equation, so that is why we had constants in this case, but that also is not required after you solve all this, right? Because particular integral don't have any arbitrary constant. Okay. So from this you will get some result that z is equal to the final result as pi as it is equal to 1 upon 39. When you solve everything, 2 cos x plus 2y minus 3 sine x plus 2y, right? Okay, this is the expression which you will get final as pi, and we know the cf, just add them, you will get the complete, that is the general solution of this question, right? So let's see reducible to PD with constant coefficients. So let's see how we will do it. So suppose, let's see, there's a question, x square del 2z by del x square minus 4xy del 2z by del x del y plus 4y square del 2z by del y square plus 6y del z by del y is equal to x cube y to the power 4. So how will you solve it? Well, so in this case, when we see such kind of problem, we will substitute x is equal to e to the power x and y is equal to e to the power capital Y, because over here we can see that the degree of the variable and the order of the expression is same. The degree is 2, order is 2. Degree is 2, order is 2. Degree is 2, order is 2. Right? Degree is 1, order is 1. So basically, if the degree of the variable is equal to the order of the derivative, then in that case, we say this, we use this substitution. So when we use this, we will have that x is equal to natural log of x and y is equal, and capital Y is equal to the natural log of x, natural log of y, right? So we get del z by del x is equal to del z by del capital X dot del capital X by del x plus del z by del capital Y by dot capital Y by capital X. But this expression is 0, so we don't need to worry. It is equal to 1 upon x del z by del capital X and del z by del y. Similarly, it will be equal to 1 upon y del z by del capital Y, right? This expression. So we can say that del z by del capital X is equal to x del z by del y, sorry, del x and del z by del y, capital Y is equal to y times del z by del y. Correct? Correct? We get this expression, right? Now we know this expression, so that is why we can say that x square del 2z by del x square is equal to del 2z by del capital X square is equal to x square del 2z by del x del small x square, right? From this expression only we can say it, right? So like this we can say for this also, and for everything else. Okay, so when you solve it you will get the whole expression. If you say this as d and this as capital D dash, then you will get the expression as d minus 2d dash of this multiplied by d minus 2d dash minus 1 is applied on z is equal to e to the power 3x plus 4y, capital Y and capital X, right? So this is how you solve for such kind of expressions. When you see the relation between degree and order of the derivative, then you can easily say what substitution you have to make. For example, in this case it was this one. Okay, so this was a basic thing which I need to tell. Now let's see non-linear PDE of second order. That is the last topic of our today's video. And heat equation and another topic I will cover in separate videos in like 5-10 minute video, because it's like totally a different topic. So that is why I will discuss in different short videos, right? So don't need to worry about that. Let me erase this. So let's discuss non-linear partial differential equation of second order. So basically it is the equation, it is a partial differential equation which includes at least R or S or T, or can include any of them, right? But it must have at least one of them, and no other higher derivative must be involved in the equation. So you can't have del 3 by some expression, you must have only R, S or T, or you can have a first order also, but R, S and T are compulsory. Not all, you can either have R, you can either have S, you can either have T, you can have R or S, you can have S or T, you can have R or T, or you can have all of them. That's no issue. But at least one should be there of R, S and T, right? So if I want to express its general form, can be given as f of x comma y comma z comma p comma q comma r comma s comma t is equal to 0, right? So we have this expression, right? Okay, so we are going to find its solution using the Monge's method. Its solution is founded by using solution by Monge's method, right? So we'll find its solution using Monge's method. Okay, so let's see it. So which form we will study? Like in that case, in Lagrange's linear partial differential equation, we studied PPQQ is equal to R. Here we will study R plus SS plus TT is equal to some V, right? Okay, where R, S, T, V are the functions of R, S, T, V are the functions of P, Q, X, Y, and Z, right? Okay, okay. So now let's see how we'll solve this expression. So using Monge's method, what we are going to do is first of all, let me erase this, then we will discuss it. So we had this equation R plus SS plus PT is equal to what? Is equal to V. We know that dz is equal to p dx plus q dy. We had derived this expression, right? And what is then dp? It is equal to del p by del x dot dx plus del p by del y dot dy. Correct? Okay. Now notice one thing, that p is equal to del z by del x. So del p by del x is equal to del 2z by del x square, right? I told this expression already, right? And similarly, del p by del y is equal to del 2z by del x del y. Okay. So this is equal to uh, r dx plus uh, yeah this okay plus t dy, okay, and similarly del q by del x dx plus del q by del y dy is equal to the expression s dx plus r dy, right? So from these two you can solve for r and s, right? You can solve for r and s. So you'll get the expression as let me erase this one. So you'll get r is equal to what? R is equal to the expression dp minus s dy by dx, and we will have t is equal to wait a minute, what I wrote, it is equal to rs plus, yeah, of course, right, it will be t, right? Sorry. Okay, so here we will get t is equal to dq. Of course, del q by del y is del 2 z by del y square, which is equal to t, not r. R is equal to del 2 z by del x square, right? Is equal to del q minus s d. Sorry, this is small s, right? Minus s dx by dy, right? This is the expression for r and t, right? And now we will substitute these value into the equation of into our this equation. So let's see what we'll get. Let me erase this. So when you substitute this, you will get r times the expression dp minus s dy by dx plus s times the expression, sorry, s is as it is. What is t? T is dq minus s dx small s divided by dy is equal to v, right? So we get this expression, and then we can simplify it, and when you simplify it you will get r dp dy plus t dq dx minus v dx dy, right? This expression minus s times r dy whole square minus s dy dx plus t dx whole square is equal to 0, right? We get this expression. Now let me see, is it fine? Yeah, okay. Now this expression is only possible, because it was derivatives and all, when this expression and this expression are 0, right? Why? Because again, I told you all, it is because they all involve derivatives, so it's not always true, because it has to be always true. So that is why this expression, these two expressions, these two coefficients have to be always equal to 0. So we get from this r dp dy plus t dq dx minus v dx dy is equal to 0, and we have r dy whole square minus s dy dx plus t dx whole square is equal to 0, right? We have these two equations which we need to solve now, right? From the coefficients, we just say, if you remember, if I say x square plus y square is equal to 0, then that is x is equal to 0 and y is equal to 0 for x and y belong to real numbers. Remember this, right? If it has to be always true, correct? Okay, that is what I'm applying over here, right? So let me erase this and let's move further. Okay, so we had this expression that r dy whole square minus s dy dx plus t dx whole square is equal to 0. Now it is something which we can factorize: square, then product, then and the square. So you can write it like this: plus is equal to 0, given that a1 b2 is not equal to a2 b2, correct? Okay, so this condition should be satisfied, and so we can say that a1 dy plus b1 dx is equal to 0, or you can say a2 dy plus b2 dx is equal to 0, and along with it the first equation must be satisfied. Which one? This one, r dp dy plus t dq dx minus v dx dy is equal to 0, and dp dy plus t dq dx minus v dx dy is equal to 0, right? So they must be satisfied, they both must be satisfied. So from this you will get the answer. So let's see a question to understand what do I mean from all this. Let me explain using a question so it will be much clearer. So let's see this question. So states r is equal to a square t. So you can say r is equal to a square t, which implies that r minus at is equal to 0. So from this we can also say that r 1 times r plus 0 times s minus plus minus a square t, sorry, it is square over here, is equal to 0. And if you compare it from the original form, that is r plus s plus t is equal to v, right? So from this we can say that r is equal to 1 and t is equal to negative a square and s is equal to 0, correct? So you remember this equation, r dy whole square plus plus minus s dy dx plus t dx whole square, right? We had this expression, remember this one? So it is equal to dy whole square, s is equal to 0, and t is equal to negative a square dx whole square, right? R was equal to 1, okay? So dy by dx whole square is equal to a square. So from this we can say that dy by dx is equal to plus minus a. We can say this expression. So we can say that y is equal to plus minus ax plus c. We can say this expression, right? So from this we can say y minus ax is equal to c1. We can say c1, or y plus ax is equal to c1, right? So these two are the expressions which we have got right now, okay? Now we remember the second equation. It was like it was r dp dy plus t dq dx minus v dx dy is equal to 0. We had this expression. So we have dp, what is the value of dy? It is equal to plus minus ay, it is equal to plus minus a, right? So instead of writing plus minus a dx, I write just a dx, so calculation becomes a bit easier, right? Okay, plus what is t? It is minus a square dq dx, v is equal to 0, so it is equal to 0. So from this we get the expression that dp is equal to a dq. We get this expression. So we get p minus aq is equal to some constant c2. Now again, since it's plus minus this expression, so we have this answer also, plus aq is equal to c2, right? Because here we had two values of dy, negative a and plus a, correct? Okay, so from all this we can say that p minus let me erase this, then I will write. So from this we can say that p minus aq is a function of y minus ax, and p plus aq is a function of y plus ax. We can say this expression, correct? So from this we can say that p is equal to 1 by 2 times the quantity f of y minus ax plus g of y plus ax. Similarly, you can solve for q also. It's just you can easily solve for these variables. It is very easy. It is just simultaneous linear equations in two variables, which you know how to solve, right? So from this you can solve for q, and then you know that dz is equal to p dx plus q dy. So from this you can say that z is equal to the integral of p dx plus q dy plus some arbitrary constant. We have this expression. So we know how to find, so we have the value of p, we have the value of q, so you can just substitute it and you will get the answer. So this is how you will solve such expressions. And there's one more thing which I need to discuss right now, and I have to be a bit fast because it's like going too long. That is why. So we had this expression RR SS TT is equal to V. So it can have it can be hyperbolic, it is hyperbolic, it is parabolic, it is elliptical if it follows such conditions. Let me tell the conditions. If it's like s square minus 4rt is greater than 0, if s square minus 4rt is equal to 0, of course these are capital variables, these are coefficients. Or if it is elliptical, if s square minus 4rt is less than 0. So let me check the conditions, are they correct? Yeah, so this, yeah, this is okay. So with this, we come to an end of this lecture, and I hope that you enjoyed this lecture. And if you did enjoy this, then please do like, share, subscribe my channel, and please support this video. And of course, the remaining portion like heat equations and all, I will cover in separate short videos. So because they are just an application of these things, so that is why I'm not covering it in one shot. And if it is required, I will cover it in some short videos. You can watch that. Okay. So if you did enjoy this video, then please do like, share, subscribe my channel, and please support this video. Bye bye. Take care, and all the best.